Righty. We are going to pick up where we left off last time then, talking about the optimal growth model. So our first kind of foray into this model was to look at a stripped down version of it that made several assumptions that are going to enable us actually to characterize the policy function analytically, which is convenient because I'll be able to show you guys some interesting solution techniques that come with this class of models. I'm going to finish that today, and then we're going to start talking about the more general optimal growth model that doesn't make those same assumptions, but nevertheless, we'll still be able to do things like characterize the optimal growth path and derive properties of the model, like the existence and uniqueness of the steady state, etc. Okay, so to kind of pick up then where we left off last time, there was a statement of the optimal growth model, and then we started to go through the various assumptions that are needed in order to establish the equivalency between the sequence problem that you're confronted with and the Bellman equation, right? The Bellman equation for this model looks like the following. So the value function of pursuing an optimal plan is equal to the max of the current return, which in this model was what? The log of k to the alpha minus k prime. That's essentially current period consumption, plus the discounted value of the continuation return, where the maximization was over this k prime. That is, we're choosing a policy function, and that policy function is constrained to live on this set G, right? Where G was defined as the closed or compact set 0 to k to the alpha. All right. So we know that this value function exists. It's continuous and bounded, and it's unique because we were able to verify assumptions 1 and 2. We started by verifying assumption 2, and the crux of that assumption is that the state variable, the relevant state variable k, the capital stock, without loss of generality, has to live on a compact set of the reals. In other words, even though the sequence problem, even though the problem that the social planner faces here does not restrict capital to be bounded above by anything, we can, without loss of generality, ensure that the state variable k lies on this closed and bounded interval. We know that k has to be some element of 0 to, what do we call it, k tilde, where k tilde, I think, was defined as the max of either initial capital or 1 in this case, which was the highest sustainable level of capital if we consume nothing forever, right? So any feasible sequence of capital stocks over time, we know have to reside on this closed and bounded subset of the reals. That was the crux of assumption 2. And because the capital stock lives on a compact set of the reals, it follows from that the utility function, because it's continuous and defined on a compact domain, is also going to be bounded. And since the utility function is bounded, we know that the value function is also going to exist, right? In other words, the overall objective function, the infinite discounted sum of period utilities over any feasible sequence of k's over time has to exist. It's going to be finite because the utility function every period is bounded for any choice of k. And so if you simply add up the maximum value at every single period, you get this finite number, right? I think we worked through that assumption in the last class. And so assumptions 1 and 2 holding means that there exists this unique, continuous, and bounded value function. In other words, we've established the existence and uniqueness of the Bellman equation, okay? Now, we also know from assumptions 1 and 2 that some optimal plan exists. In other words, there's a way for the planner to choose a sequence of capital stocks over time that achieve the optimal value of the Bellman equation. We do not know, however, yet, that a unique optimal policy exists, right? What we'd like to start doing today is determine, or prove that is, that there is some optimal policy function that takes the form of a time invariant function of the state variable, pi of k, let's say. And by implementing this policy function, the planner can achieve the value function, or the optimal value of the plan. Okay, so how do we do that? We basically need to establish two things that are contained in, I believe it's assumption 3. In order for this maximization problem to generate a unique extremum, the value function itself needs to be strictly concave. And the constraint correspondence, G, needs to be convex. All right, that's what I want to start off doing today, is proving or demonstrating that the value function is strictly concave, which follows from the period utility function being concave, as well as the constraint correspondence being convex, right? That's assumption 3, which gives us, I believe it was theorem 4 and this matching corollary, which enables us to prove the existence of this unique policy function. Okay, now some of you may be looking at this already and saying, well, a logarithmic utility function, that is a concave function. Well, it's concave in consumption, but I don't believe it's perfectly clear that it's concave in k prime, right? Remember, the utility function here is a function of the state and the control. So we want to demonstrate that that utility function is concave in its two arguments, the state and the control. So how do we do that? Let's work through this. So we're going to take two values of k, k1 and k2, and we're going to assume that they're not equal to one another. Okay? K1 prime then is simply an element of g of k1, and k2 prime is an element of g of k2, right? So we're going to take 2 points in the state space, and how do we prove the concavity of the utility function? With respect to k prime, you evaluate utility at a convex combination of the two, and that has to be greater than the linear combination of the utility functions evaluated at these two separate points, right? So the first step then is to write what is utility evaluated at this linear combination of 2 points. Let's take some parameter phi between 0 and 1, okay? It could be 1/2 if you want it. Then the utility function depends, remember, on k and k prime. So let's take the combination of these 2 points, k1 and k2. So it would be what? Phi k1 plus 1 minus phi k2. That would be the first argument. The second argument would, of course, be phi k1 prime plus, 1 minus phi k2 prime. All right, now what's that equal to? Well, we've got a logarithmic utility function. So that's the log of, let's see, the first point here, it would be phi k1 plus 1 minus phi k2, that whole argument to the alpha, that's my new value of k, this combination between these 2 points, minus k prime. Well, that's minus phi k1 prime plus 1 minus phi k2 prime. Right? All right, I'm going to argue that the log of this combination of 2 points here has to be bigger than the log of phi k1 to the alpha plus 1 minus phi k2 to the alpha, and then minus phi k1 prime minus 1 minus phi k2 prime. In other words, what I'm saying here is that this term, this phi k1 plus 1 minus phi k2, the whole quantity to the alpha, is going to be bigger than this term, phi k1 to the alpha plus 1 minus phi k2 to the alpha. Now, why is that? Some of you may see that really quickly. That's because the production function, k to the alpha, is strictly concave. If you don't believe me, let's just draw it and prove the case. What does k to the alpha look like? Like this, right? Let's take our 2 points. Let's take a k1 and a k2. So this is k1 to the alpha. This is k2 to the alpha. Let's take a point between k1 and k2, which is phi k1 plus 1 minus phi k2, right? If phi is 1/2, it's exactly halfway between the two. What is this point then? That would be phi k1 plus 1 minus phi k2, all of that to the alpha, right? Well, you'll notice that because the production function here is concave, that this point is bigger than this point, right? And what does this point correspond to? Well, that is, what is that? That would be the average of k1 to the alpha and k2 to the alpha, right? It's phi k1 to the alpha plus 1 minus phi k2 to the alpha. So because k to the alpha is concave, phi k1 plus 1 minus phi k2 quantity to the alpha has to be bigger than the combination of those two, phi k1 to the alpha plus 1 minus phi k2 to the alpha. So this is going to be bigger than this, basically because the production function is strictly concave. You guys follow? Okay, now what is this equal? Let me continue with this argument over here. What is this equal to? This would be the log of phi times k1 to the alpha minus k1 prime plus 1 minus phi times k2 to the alpha minus k2 prime. Well, that to me just looks like the log of phi times c1, if we define c1 as k1 to the alpha minus k1 prime, plus 1 minus phi c2. By the same argument that I just used here on the production function, I know that the log of phi c1 plus 1 minus phi c2 has to be bigger than phi times the log of c1 plus 1 minus phi times the log of c2. The logarithmic function has the same shape as k to the alpha, right? So because the utility is strictly concave in consumption, we know that this inequality holds, as long as c1 is not equal to c2. Well, what is phi log of c1 equal to? That's just phi times the log of k1 to the alpha minus k1 prime plus 1 minus phi times the log of k2 to the alpha minus k2 prime. And that, of course, is just phi u of k1, k1 prime, plus 1 minus phi u k2, k2 prime. And there you go. The canonical logarithmic utility function in the growth model here will be strictly concave in k prime. Therefore, the value function is going to be strictly concave. Well, hold on. We got to prove one other thing first, right? And that is that the constraint set G is convex. That's pretty easy to do. How do we prove that? Again, let's consider these 2 points here, K1 and K2, with a K1 prime and G of K1, and a K2 prime and G of K2. And also let's take some phi between 0 and 1. Well, and remember how we prove convexity. If you take this linear combination of controls, K1 prime, K2 prime, that has to live inside of the constraint set defined by the linear combination of the 2 points, K1 and K2. All right, go back and take a look at the definition of what a convex set looks like. So how can we prove that? Well, first off, we know because K can never be negative, we know that 0 has to be less than or equal to phi K1 prime plus 1 minus phi K2 prime, right? Well, that has to be less than or equal to phi K1 to the alpha plus 1 minus phi K2 to the alpha. Now, why is that? K1 prime can never exceed K1 to the alpha. That's the highest value it can take on this constraint set G. So the sum of these two things here must be bounded above then by phi K1 to the alpha plus 1 minus phi K2 to the alpha. Now we know that this is going to be strictly less than the following. Phi of K1 plus 1 minus phi of K2, the whole thing to the alpha. And why do we know that? Because K to the alpha is a convex function. We just use that in our demonstration above. This point here, phi K1 plus 1 minus phi K2 to the alpha, that of course resides inside of the constraint set defined over phi K1 plus 1 minus phi K2, right? That constraint set is just 0 to phi K1 plus 1 minus phi K2 raised to the alpha. So this linear combination of points here is going to lie inside of the constraint set defined by the same linear combination of K's. So G is also convex. Therefore, V is strictly concave. And it will follow from that then that the optimal policy function, pi, is indeed a function and not a correspondence. There's going to be a unique way for the planner to pursue an optimal policy. There will not be more than one possible path that leads to the highest value for lifetime utility. Okay, questions so far? So I've demonstrated concavity and convexity of the utility function and the constraint correspondence. When we move on later today and into the next class to talk about the general optimal growth model, I'm not going to reprove these two things for the general case, all right, where I've just got a regular utility function and a regular production function. It's not necessarily Cobb-Douglas, but the proof works exactly the same. So if you can do it here, you can do it in the general case as well.
One question.
Yeah.
So could we show that the reduction function is concave? Would that be sufficient to imply that the utility function is concave?
I think so. The utility function is concave in consumption. That's an assumption 6, I believe, right? Utility is increasing in consumption and also strictly concave. It's not clear to me though that it's necessarily concave in K prime, given the way K and K prime appear in the utility. It's a unique, in the optimal growth model, it appears as K to the alpha minus K prime, or it appears as F of K plus 1 minus delta K minus K prime. So it enters the utility function in a particular way because consumption is related to capital in a particular way in the resource constraint. So I think you have to go one step further and show that it's actually concave in K prime. And it doesn't necessarily follow directly from F being concave in K. But you do use that in the proof though, right? Okay, before we get on to the actual analytic solution to the canonical growth model, there's a couple of other assumptions I want to establish that are going to be useful for us. It will be useful for us to ensure that the value function is strictly increasing in the state. So that if the capital stock, if the endowment of capital were to increase, the lifetime utility function would increase, the value function would go up. How do we establish that result from our dynamic programming theorems? It requires two things. It requires that the utility function be strictly increasing in the state, and that the constraint correspondence be monotone, right? Well, that's assumption 4. So let's quickly just verify that. And I'm going to assume, again, that the utility function is differentiable here to make life easy for us. What is the partial of the utility function with respect to K equal to? Hopefully it's positive, but we know what it is. We actually have a functional form for it, right? The utility function is the log, right? Remember what U of K prime K is. It's the log of K to the alpha minus K prime. So the partial of U with respect to K would be equal to what? It would be, let's see, 1 divided by K to the alpha minus K prime times, chain rule, alpha K to the alpha minus 1, right? Well, can we sign that? Alpha K to the alpha minus 1 is definitely a positive number, correct? What about the denominator? K to the alpha minus K prime. What's the sign of that? It's positive. K prime can never be bigger than K to the alpha, right? That's the limit on what K prime can be. This is basically just C, right? The consumption has to be positive. So this is a positive over a positive, giving you a positive. So the utility function is indeed increasing in the state. You increase and this makes sense, right? If you increase the capital stock, output from the production function is going to go up, right? And if output goes up, you'll be able to consume more. And if consumption goes up, you'll be able to enjoy more utility, all right? So the utility function here is increasing in the state. That's critical to establishing that the value function itself is increasing in the state. Is G monotone? What does it mean to be a monotone set mapping or correspondence? And we can't answer this question unless we know what these words mean. A function is increasing, if you increase the variable, and it increases the function value, right? But it's a set valued correspondence doesn't have exactly the same meaning, right? Because there's multiple values within G for a given value of K. But what do we mean by G being monotone? If we increase the value of K, we expand the set of possible values for K prime, right? So let's take a K1 and a K2 that are both inside of the range of possible values for K here between 0 and K tilde, but where K1 is strictly less than K2. What's G of K1? That's defined by the set 0 to K1 to the alpha, right? Well, you'll notice that that is fully contained in the set defined by 0 to K2 to the alpha, because K2 is bigger than K1. Well, this set 0 to K2 to the alpha is, of course, just G of K2. So increasing the state from K1 to K2 increases G of K2. G of K2 fully swallows up G of K1. So G indeed is a monotone mapping. Therefore, the value function V is strictly increasing. One more assumption very quickly here. And I really already assumed it in the last demonstration. The utility function U of K, K prime, is going to be continuously differentiable on the interior of its domain, right? On the interior of its domain, where hopefully you guys remember this, the domain of U is defined as the set of all K primes such that K prime is feasible. So U is continuously differentiable on the interior of its domain. It's going to follow then that the value function will be continuously differentiable. Now, if we identify the optimal policy function, pi, what is the value function equal to? In this case, it is equal to the log of K to the alpha minus pi of K, that's K prime, plus beta times V of K prime, which is pi of K. If we want to take the derivative of the value function with respect to the state, because we know that the utility function is continuously differentiable, then we simply appeal to the envelope condition, right? And what does that say in this case? That V prime of K is going to be equal to alpha K to the alpha minus 1 over K to the alpha minus pi of K. We do not have to consider, that is, how K affects K prime optimally through pi. That's the whole point of the value function. Okay, any questions then about the assumptions? All that makes sense? All right, let's spend a while now, perhaps the rest of the class, I'm not sure how long this is going to take me, actually demonstrating how to solve analytically for the policy function in this problem, okay? So again, let's set this up right. The social planner is confronted with an optimal sequence problem, right? That was, well, we wrote it down in the last class, right? It's to maximize over a sequence of capital stocks the discounted sum of period utilities subject to a resource constraint where the capital stock can't be negative. We have now established all of the things necessary in order for the sequence problem and the Bellman equation to give us the same solutions. These are equivalent ways of solving this problem. So the central planner sets up the Bellman equation for this model. And again, it's V of k is equal to the max of k prime on 0 k to the alpha, that's g in this case, of the log of k to the alpha minus k prime plus beta v of k prime. This holds for any possible value of the state variable that is on this closed and bounded interval that we identified earlier. So this is part A of the problem. Set up the recursive form of this sequence problem. You have to be able to do this, okay? Now, what we want to do is derive the analytic solution for the policy function, okay? So we want to try to find the optimal value of k prime, which can be represented as some time invariant policy function of the state. This shows how the planner takes the current value of the state and decides what the value, the optimal value of the control is going to be every single period. This is really the object of our interest here. In most real applications, one cannot solve for pi analytically. The value of doing this canonical version of the model is that we can, okay? All right, so how do we do that? Well, like any maximization problem, we want to evaluate the first order condition, right? That's where we start. So what is the first order condition here? We want to take the derivative with respect to the control, k prime. Well, let's do that. Where does k prime show up in the maximization problem? Right here in the current return and right here in the continuation return. So it would be what? A 1 over k to the alpha minus k prime times -1, chain rule, plus, let's see, beta v prime, the derivative of v with respect to k prime. The first order condition sets that term equal to 0. Now, of course, it's only going to equal 0 at the chosen optimal value of k prime, that is k prime star, let's say. We know that the value function is strictly concave. So if we can find a k prime that satisfies the first order condition, it's also going to satisfy the second order condition. So we don't need to verify second order conditions here. What's the problem with this first order condition? In a regular single variable calculus class, you can solve for this maximization problem from the, or even in your micro class, you could solve for the control here directly from the first order condition, right? Why can't you do it here? Why is this problem difficult? Why can't I solve directly for k prime in this first order condition?
We have a derivative of the value function with respect to k prime. So
Exactly.
yeah,
What the hell is that? We don't know what v is. V is the thing we're trying to maximize. Y'all get this? It's a maximization problem that is defined recursively. The thing we're maximizing has as one of its arguments, right-hand side arguments, the maximized value of the thing itself. How do I get rid of a value function argument in this class of maximization problems? I want that out of here. I don't want any value function arguments in my first order condition. Envelope condition. I'll chalk this up to the fact that you guys have an econometrics exam coming up. Is that right? Or did you already take it?
Yeah, tomorrow.
Okay. The envelope condition. So first set up the Bellman equation, then derive the first order condition. To get rid of this value function term, you've got to evaluate the envelope condition, right? This is just a derivative of the value function. Well, what's v prime of k? Well, that's just alpha k to the alpha minus 1 over k to the alpha minus k prime star, right? The envelope condition is evaluated at the optimal value of the variable you're maximizing here. Now, what is k prime star? That's given by our optimal policy function, pi of k, right? That's the thing we're trying to find. Okay, now, given these two pieces of information then, remember theorem 8 or 7 from the last section of the course? What two things characterize the solution to an infinite horizon problem? The intertemporal Euler equation and the transversality condition. We'll write the transversality condition later. How do we get the intertemporal Euler equation? You substitute the envelope condition back into the first order condition. But you have to be careful. Notice the dating difference here. The envelope condition has v prime of k. The first order condition has v prime of k prime. So you have to scroll the envelope condition forward one period before you substitute it in there. And what are you going to get then for the Euler equation? Well, it's going to be, I'm going to swing this thing to the other side. It's 1 over k to the alpha minus k prime star, that's pi of k, is equal to beta times v prime of k prime. Well, what is v prime of k prime equal to? Okay, that's going to be alpha times k prime to the alpha minus 1. Well, what's k prime? It's pi of k to the alpha minus 1, divided by k prime to the alpha. So that's pi of k to the alpha. Oh God, now what do we do? Minus pi of k prime. Well, that's pi of k. Now we have an Euler equation that no longer depends on the value function. That doesn't mean that we can solve it easily, though. Why? Because really the thing we're trying to find is not the value of a variable, let's say k prime, but we're actually trying to solve for a function. It's a functional equation, not a regular equation, right? You're not trying to find x or y here. You're actually trying to find a particular function. There's no good way of solving these types of problems that I know of that are actually solvable other than using something called the method of undetermined coefficients, or sometimes it's just called a guess and verify strategy. In other words, we want to guess a functional form for pi and then determine explicitly what that function is by substituting in our guess. Does that make sense? So let me show you how that's done here. We're going to guess a particular function for k prime. Now, what should be a good guess? We're going to guess right, okay? You guess wrong, this won't work. This only works if you can guess right. Well, I'll just tell you that in this class of dynamic programming problems, the correct functional form, for ones that are solvable analytically, the correct functional form is going to be something that looks similar to the production function, which is the key piece of the resource constraint. The production function is a k to the alpha, right? So I'm going to guess that k prime is going to take the following form. I'm going to guess that it's going to be equal to some unknown coefficient, let's call it a, times k to the alpha. That's going to be my guess. Now what I want to do is I want to plug this guess into the Euler equation and then see if I can't figure out what this undetermined coefficient is, a. If I can determine that and everything equals, then I'm going to have figured out what the policy function is. Okay, so let's do that. Again, let's be careful about this. The left-hand side of the Euler equation becomes 1 divided by k to the alpha minus pi of k, that's a k to the alpha. The right-hand side is beta times alpha pi of k to the alpha minus 1. Well, that's going to be a k to the alpha quantity to the alpha minus 1 over pi of k to the alpha. So that's a k to the alpha raised to the alpha minus pi of k. All right, now be really careful about this. This would be a times k prime to the alpha. So that would be a k to the alpha, and then the whole thing raised again to the alpha. So I've done nothing more than substitute my guess into this Euler equation. And now I'm going to try to solve this little equation for a. So let me simplify the left-hand side. It's a 1 minus a times k to the alpha. Now, fortunately, lots of things cancel over here on the right-hand side. Here's an a k to the alpha raised to the alpha. That cancels here, here, and here. And you're left with a beta times, let's see, alpha, a k to the alpha minus 1 over a 1 minus a. This 1 minus a cancels with this 1 minus a. And then you get a 1 over k to the alpha is equal to, let's see, alpha beta divided by a k to the alpha. The k to the alpha terms cancel. Oh, look at that. A is equal to alpha beta. Isn't that nice? Therefore, if we want to reinsert time subscripts, the optimal value of kt plus 1 is going to be equal to alpha beta times kt to the alpha. And the optimal value of ct then can be obtained directly from the resource constraint. And it will be equal to 1 minus alpha beta times kt to the alpha. There are the optimal policy functions then in the growth model. So this is, if you want to, in the context of the solo model, we derived a fundamental law of motion for capital that showed how kt maps into kt plus 1. And we analyzed the steady state properties and the stability properties of that equation. In the OLG model, we solved a 2-period maximization problem to derive the savings function for agents. And we use that savings function to derive the law of motion for capital in the economy. And given certain restrictions, we can, like the ones that you had on your exam, you can show that kt plus 1 is some function of kt. Here's an infinite horizon growth model, but we're going to use dynamic programming and a guess and verify strategy to solve for the law of motion or optimal policy function for capital that shows how kt maps into kt plus 1. Okay, but the way it does it here is based on underlying infinite horizon optimization principles, right? The solo model doesn't have any optimization that it comes from. Okay, y'all have any questions about that? All right, a few more things here. Sometimes I'm going to want you to solve for the value function. That might be of independent interest. I think the policy function is the most important, but occasionally knowing what the value function is will also be important. How do you do that? Well, what is the value function equal to? Again, all this stuff now should just be almost second nature. You know what the value function looks like, right? It's the current return, the log of k to the alpha minus k prime, which is pi of k, plus beta times v of k prime, which is pi of k. Now we know what pi of k equals, right? Pi of k is alpha, beta, k to the alpha. So we can substitute that in then to the Bellman equation, and what we're going to be left with then is a functional equation in v, right? You'll have v of k is equal to the log of k to the alpha minus alpha beta k to the alpha plus beta v of alpha beta k to the alpha. Well, we just got done solving a functional equation by using a guess and verify method. Why don't we do the same thing for the value function? All right, so what is my guess going to be this time? Well, here, let me give you another piece of advice. The policy function is always going to look like the production function, or is going to resemble what is in the resource constraint. The value function is going to look like the utility function, because the value function is just this infinite sum of utility functions. Well, what class of utility functions are we working with here? Logarithmic utility functions. So I'm going to guess a value function that takes the following form. Let's say some constant e plus some constant capital A times the log of the state variable k. Remember, the value function is just a function of the state. I'm going to guess a logarithmic value function because the utility function is also logarithmic. Okay, let's see if that will work. And that is what we want to do then is solve for these undetermined coefficients e and a. All right, if v of k is equal to e plus a log of k, then we can substitute that into the left-hand side of the Bellman equation. What is the right-hand side of the Bellman equation? Well, it's the log of k to the alpha minus pi of k. That's alpha beta k to the alpha plus beta times v of pi of k. Well, what's v of pi of k? That's going to be equal to e plus a times the log of pi of k, which is alpha beta k to the alpha. Okay, can we simplify or group terms on the right-hand side? This first logarithmic expression can be broken into two parts. It's the log of 1 minus alpha beta plus alpha times the log of k. All right, you factor out a k to the alpha from that sum, and then bring the alpha down because of the log rule, plus beta times e plus beta times a I can do something similar here. Break this log expression between the log of alpha beta and alpha log k. See how that works? Now we can do what? We can match coefficients, right? The intercept term on the left-hand side must equal the sum of the intercept terms on the right-hand side. The coefficient on log of k on the left-hand side has to equal the sum of the coefficients on the log of k on the right-hand side. Well, let's do that one first. If we match coefficients here, we see that the term a has to be equal to alpha plus alpha beta a. You guys follow? So this a log of k term has to be equal to alpha log k plus beta a alpha log k. Therefore, the coefficients have to be equal to one another. That's why I call it it's sometimes referred to as a matching coefficients method. Well, we can solve this for a, right? A is equal to alpha divided by 1 minus alpha beta. Well, there's one of them. That's easy to do. And that's actually the more important one. E is just a stupid intercept term, but if you want to solve for it, you can do that. E has to be equal to what? Well, what are the intercept terms on the right-hand side? Log of 1 minus alpha beta plus beta E plus beta A times the log of alpha beta. We'll swing the beta E to the left-hand side and then divide by 1 minus beta, and you get that E is equal to 1 over 1 minus beta times quantity log of 1 minus alpha beta plus beta A times the log of alpha beta. Well, A is alpha over 1 minus alpha beta. So this would be alpha beta over 1 minus alpha beta times the log of alpha beta. And there is your E term. You see how the undetermined coefficients here really just depend on two underlying parameters, the Cobb-Douglas production parameter and the discount rate, or the discount factor. So V of k then is equal to this term E, all right, which is this long intercept term, plus alpha over 1 minus alpha beta times the log of k. You know, any questions about that? Okay, so there should be several review questions that you guys can practice. There's a certain family of utility functions and production functions, or a certain class of problems where analytical solutions are obtainable. One is the Cobb-Douglas production log utility class. Another is kind of a power utility function, or CRRA utility, with a linear production function. The class of linear quadratic models is also solvable. That is where you have a quadratic utility function and a linear production function, or linear constraint. I also think there's a weird class of like exponential utility functions that's solvable analytically, and maybe one or two more. You can find those out there. I may have those review questions online. I would practice these using different functional forms. It's not my my goal is not for you guys to memorize or learn all the different guess and verify strategies for each of these class of problems. That's not really the goal here. I want you to understand how these types of models are solved. If I give you a sequence problem, how you set up the Bellman equation, the steps involved in characterizing the solution to that Bellman equation, okay? So work through those problems, and I focus on different cases that are solvable analytically to reinforce those basic concepts, okay? A lot of them are canonical versions of the growth model. So log preferences, Cobb-Douglas production, okay, or something similar. There's certain twists you can put on the problem to give you various different solutions, but it all illustrates the same basic concept. Okay, one last thing I want to do today before we quit. So again, there are two criteria that need to be satisfied by an optimal solution to one of these sequence problems. One is this intertemporal Euler equation, and the other is the transversality condition, okay? So what I want to do is establish that the transversality condition is actually satisfied in this canonical growth model, okay? And that's pretty straightforward to do. First off, so the policy function kt plus 1 we've determined was equal to alpha times beta times kt to the alpha. That defines a mapping between kt and kt plus 1. That mapping implies a steady state, does it not? Just like the solar model. What is the steady state that comes out of this model? Well, k star is equal to alpha beta k star to the alpha, right? So k star to the 1 minus alpha is equal to alpha beta, which means that the steady state value of capital should be equal to alpha beta raised to the 1 over 1 minus alpha. So the canonical growth model admits a unique steady state level of capital that we've found analytically, and it follows directly from this policy function. Very straightforward. Let's use this information to verify that indeed the transversality condition will be satisfied. What is the transversality condition? You need to know what that is. I'll ask you on an exam to write down the list of equations that characterizes the solution to one of these problems. One of them is the transversality condition. So what does it look like for this model? Well, I'll give you a hint. It starts with a limit as t goes to infinity of something.
Beta times the value function.
Beta to the t, the discounted value way out at infinity, to boy, times, say it again.
The derivative of the value function with respect to the control variable. In this case, it would be.
Okay, be careful. It would be the derivative of the value function with respect to the state, or alternatively, it's the, because of the envelope condition, it's the derivative of the utility function with respect to the state, all right, times the value of the state. That product way out at infinity has to limit to 0, right? So it's what's the derivative of the utility function with respect to the state? Well, we did this already. It's alpha kt to the alpha minus 1 over kt to the alpha minus kt plus 1. And by the way, these have to be evaluated at the optimal sequence for the k's, so kt stars, times kt is equal to 0. Well, does this thing actually limit to 0? Well, sure it does, right? We know that in the long run, k approaches a steady state value, k star. So this limit expression can be rewritten as the limit as t goes to infinity of beta to the t. Let's see, alpha k star to the alpha minus 1 times k star would just be alpha k star to the alpha divided by k star to the alpha minus k star. If I divide everything by alpha, or if I divide everything by k star, that's just the limit as t goes to infinity of beta to the t, alpha k star to the alpha minus 1 over k star to the alpha minus 1 minus 1. This whole term here doesn't really depend on time. It can be pulled out of the limit expression, and you're left with a constant times a limit as t goes to infinity of beta to the t. Beta is less than 1, so this whole thing is going to be equal to 0. Okay? Oh, sorry. Yeah. So the transversality condition will hold trivially in this model, and it's because the capital stock converges to this steady state. In a more general model that you cannot solve analytically, you would need to write down the transversality condition along with the Euler equations in order to characterize the equilibrium of the model. Okay, you guys have any questions about that then? Let me just state, I'm not going to get into this today, but just to set this up for the next class. We're now going to go back to the baseline optimal growth model. So we're not going to be willing to make these strong assumptions on utility and production, okay? And let's instead assume that the planner is faced with the following sequence problem. Maximize over an infinite sequence of capital and consumption the sum from 0 to infinity, beta to the t, u ct, subject to the resource constraint. Well, now what does the resource constraint look like for the planner? Kt plus 1 is going to be equal to f of kt plus whatever capital remains after depreciation minus consumption, where kt has to be non-negative and the initial value of capital is given. So this is the statement of the kind of the standard baseline optimal growth model. All right. We're going to make standard assumptions about the production function. It is neoclassical. So it is increasing in the capital stock, but at a diminishing rate, and it satisfies the Analytic conditions. It's increasing, strictly concave, it satisfies the Analytic conditions. I'll save this for next time, but we're going to make one small modification to our assumption about the utility function. So it's, in general, it's going to be increasing in consumption and strictly concave and continuously differentiable. We're going to make one small additional assumption about it that is actually going to help us improving the stability of the growth path in this model a couple class periods from now. Okay, but here's where we're going to go with this. So we're going to state the baseline optimal growth model. Okay, what is step one then? We want to convert this sequence problem into a Bellman equation. And then we want to make sure that solving the Bellman equation is equivalent to solving the sequence problem. Okay? Basically the one assumption that all of this stuff hinges on is whether or not the capital stock resides on this closed and bounded set. So I want to go and reestablish that for the general case and show that K and D does live on a closed and bounded set of the reals. That particular set looks a little different than it does in the canonical model. From that, it will follow that the utility function is bounded, the objective function is going to exist. All that other stuff follows from that. And I'm not going to go through all of those arguments again. We'll immediately go into some propositions on various properties of the optimal growth model that are going to be useful for us. All right, and we'll characterize the equilibrium of the growth model and then look at its steady state and its stability properties. I anticipate that taking 2 more classes, and then we'll probably be finished with this material. Okay, at which point we'll stay on this theme and discuss the neoclassical growth model, which maximizes the same set of objectives, but this time from the perspective of individuals rather than a central planner. So instead of an aggregate resource constraint, we're going to be constrained by our income flows. All right. The allocations, the solutions that come out of that model will be identical to these, but it's going to be somewhat more complicated by the fact that we've got a competitive equilibrium environment instead of this central planner type environment. Okay. But there's going to be some tools that are developed in the context of that version of the model that are useful and different than the analysis that we present here. That'll take at least 2 weeks to go through, and then we'll have your next exam. I'm kind of looking down the road, and it's probably early November would be your second exam at this point. Like maybe that week of November 4th, 5th, or 6th, something like that. Okay, you guys have any last questions then about what we did today?